Have you ever gazed up at the night sky and wondered about the origins of the galaxies that sprinkle it with light? This is the question that has intrigued astronomers, scientists, and curious minds for centuries. The cosmos is a vast, mysterious place, hiding its secrets in the distant galaxies that we see through our telescopes. It has sparked countless theories about how these galaxies came to be, each more fascinating than the last. From the role of dark matter in shaping galaxies to the possibility of galactic collisions and mergers, we'll delve into the top 10 theories that seek to explain the origins of these celestial bodies. But remember, as we journey through these theories, the universe keeps its secrets well. There is still so much we don't know, and perhaps so much we may never know. So, buckle up, space enthusiasts, and join us as we count down the top 10 theories about the origins of galaxies. Starting at number 10, we have the primeval atom hypothesis. This theory suggests that the universe began as a single, incredibly dense atom. Imagine, if you will, all the matter, energy, space, and time of the cosmos, compressed into a point of almost infinite density and temperature. This primeval atom then exploded, expanding and cooling over time to form the universe we see today. In the mid-20th century, the primeval atom hypothesis was quite popular. However, it has since fallen out of favor, mostly due to the lack of empirical evidence and the rise of other theories that better fit our observations of the universe. Yet, despite its decline, we should not underestimate the importance of the primeval atom hypothesis. It was instrumental in the development of modern cosmology, sparking debates and inspiring new ideas about the origin and evolution of the universe. While no longer widely accepted, the primeval atom hypothesis paved the way for many of the theories we'll explore next. Next up, at number 9, is the steady-state theory. This theory suggests that the universe has always existed in the state we observe today and will continue to do so indefinitely. It's a concept that defies the notion of a beginning or an end. The universe simply is, always was, and always will be. But hold on, you might be wondering, if the universe is expanding as we know it is, then how can it remain in a steady state? The theory resolves this by proposing the continuous creation of matter to maintain a constant density as the universe expands. However, the steady-state theory has been largely dismissed by the scientific community. Why? Primarily because it contradicts the observed evidence of an evolving universe, such as the discovery of cosmic microwave background radiation, which supports the Big Bang theory. Despite its lack of acceptance today, the steady-state theory played a key role in shaping our understanding of the universe. Coming in at number 8, we have the oscillating universe theory. This theory suggests a rather rhythmic view of the universe's existence. Imagine the universe as a cosmic accordion, expanding and contracting in a never-ending cycle. The expansion phase is what we commonly refer to as the Big Bang, a moment of explosive growth. Conversely, the contraction phase, known as the Big Crunch, sees all matter and space-time collapsing back into a singular point. So why isn't this theory widely accepted? Well, it's quite simple. Current evidence, such as the observed rate of cosmic expansion, doesn't fully support these cyclical events. Furthermore, the theory doesn't quite explain the origin of the initial singularity or the cause of its cyclical nature. While the oscillating universe theory may not be the most popular, it certainly is one of the most fascinating. At number 7, we find ourselves in the realm of the multiverse theory. Let's step into a world beyond our own, where our universe is merely a single page in a vast cosmic library. The multiverse theory proposes that countless universes exist, each with its own laws of physics and unique galaxies. Imagine an infinite expanse of universes, each birthing galaxies in ways we might not even be able to comprehend. This theory could potentially explain the diverse array of galaxies we observe, as each universe might have a different recipe for galaxy formation. However, it's important to note that this theory isn't widely accepted. The primary reason being, it's almost impossible to test or validate. We can't exactly hop into a spaceship and visit these other universes to verify their existence. The multiverse theory may be controversial, but it opens up a world of possibilities. Moving on to number 6, we delve into the quantum fluctuation hypothesis. This theory posits that our universe, and by extension galaxies, sprang into existence from a quantum event. In the weird and wonderful world of quantum mechanics, particles can pop in and out of existence, seemingly from nowhere. Imagine then a tiny speck, a quantum fluctuation, bursting forth to create a whole universe. However, this hypothesis is not as widely accepted as others. Critics argue that it's too speculative, relying heavily on the principles of quantum mechanics, a field still riddled with mysteries. Others question how a quantum event could lead to the creation of a universe that appears fine-tuned for life. Despite these reservations, the quantum fluctuation hypothesis opens up fascinating possibilities. It suggests a universe that is not just born out of chaos, but from the intricate dance of quantum particles. The quantum fluctuation hypothesis may be complex, but it offers a compelling explanation for the origins of galaxies. Crashing in at number 5 is the galactic collision theory. Now, this theory takes us on a cosmic rollercoaster ride. It suggests that galaxies, as we see them today, were not always the majestic spirals or elliptical giants. Instead, they started as smaller structures, which over time collided and merged, forming the grand galaxies we see today. Imagine two cosmic bodies, hurtling through the vast expanse of space, pulled together by the unyielding force of gravity. Upon collision, these smaller structures merge, their stars jostling and rearranging, eventually settling into a new, larger galaxy. Evidence supporting this theory comes from our very own cosmic neighborhood. The Andromeda Galaxy and our Milky Way are on a collision course, set to merge in about 4 billion years. Observations of such impending collisions in the cosmos lend weight to this captivating theory. The galactic collision theory gives us a dynamic and violent picture of the universe's history. Dark and mysterious, coming in at number 4 is the dark matter theory. This elusive theory suggests that the galaxies we see today were sculpted not by the visible matter, but by the invisible substance known as dark matter. Imagine a cosmic ballet, where galaxies are dancers and dark matter, the unseen choreographer. Dark matter, although unobserved directly, makes up about 85% of the universe's total matter. It doesn't interact with light, making it virtually invisible, yet we know it's there. How so? Through its gravitational effects on visible matter, such as stars and galaxies. In essence, it's the invisible glue that holds galaxies together. Scientists believe that dark matter's gravitational pull guided the ordinary matter into forming galaxies. The clustering and web-like structure of galaxies we observe today echo the distribution of dark matter in the universe, providing a compelling testament to this theory. While we can't see dark matter, its influence may have shaped the universe as we know it. Exploding onto the scene at number 3 is the Big Bang theory. This well-known model of cosmic genesis posits that our universe began as an extremely hot and dense point, roughly 13.8 billion years ago. In an event known as the Big Bang, this minute singularity began expanding rapidly, ultimately giving birth to all the matter and energy we observe today. Over time, the universe cooled and expanded, allowing subatomic particles to form and eventually coalesce into atoms. Gravity pulled these atoms into massive clouds, which collapsed under their own weight, forging stars and galaxies. Evidence for the Big Bang theory comes from many quarters. The most compelling include the observed cosmic microwave background radiation, which is the afterglow of the Big Bang, and the redshift of distant galaxies, indicating that the universe is still expanding. The Big Bang theory may be well known, but it's not our final contender. So stay tuned as we unveil the top 2 theories of galaxy formation. Expanding our understanding at number 2 is the cosmic inflation theory. This theory is a fascinating addition to the Big Bang theory, proposing that just after the initial explosion, the universe expanded at an exponential rate. Imagine the universe inflating like a balloon in less time than it takes to blink. This rapid expansion smoothed out the cosmos, leading to the uniform universe we observe today. Now, what evidence backs this theory? The answer lies in the cosmic microwave background radiation. This radiation is remarkably uniform across the sky, but it contains tiny temperature fluctuations. These fluctuations align perfectly with the predictions of the cosmic inflation theory, adding significant weight to its validity. What does this mean for the origins of galaxies? Well, during this period of inflation, quantum fluctuations could have been stretched into macroscopic size, providing the seeds for galaxy formation. The cosmic inflation theory takes the Big Bang a step further, providing a more complete picture of the universe's history. And finally, at number 1, we have the hierarchical structure formation theory. This theory is the reigning champion when it comes to explaining the origin of galaxies. It suggests that galaxies weren't formed in one grand cosmic event, but rather through a slow and steady process of accumulation. Think of it like building a castle, not from a single giant block of stone, but from countless smaller bricks, carefully stacked together over time. The hierarchical structure formation theory proposes that small structures, such as globular clusters and dwarf galaxies, formed first in the early universe. These tiny structures, bound together by gravitational forces, began to merge and grow, eventually forming larger and larger structures. Over billions of years, this process led to the formation of the galaxies we see today. Vast collections of stars and gas, all held together by gravity. This theory is supported by a wealth of evidence. For instance, when we look out into the universe, we see galaxies in all stages of development, from small young galaxies to massive mature ones. This is exactly what we'd expect if galaxies formed gradually over time, rather than all at once. Furthermore, computer simulations of the universe, which take into account all known physical laws, consistently produce galaxies that look remarkably like the ones we observe. These simulations start with a universe filled with small structures and let them interact and merge over billions of years. The fact that these simulations produce realistic galaxies gives us confidence that the hierarchical structure formation theory is on the right track. But of course, no theory is perfect. There are still many questions to answer and mysteries to solve when it comes to the formation of galaxies. However, the hierarchical structure formation theory currently provides the most compelling explanation we have. The hierarchical structure formation theory may not have all the answers, but it currently provides the most compelling explanation for the origins of galaxies. And there you have it, the top 10 theories about the origins of galaxies. We've journeyed from the primeval atom hypothesis to the steady-state theory, and even through the oscillating universe theory. We've explored the possibilities of a multiverse and the quantum fluctuations that could have sparked our universe's existence. We've seen galaxies collide and the role of the elusive dark matter. We've revisited the Big Bang and the expansive reach of cosmic inflation. And finally, we've delved into the hierarchical structure formation theory, where galaxies are built from the ground up. In this vast cosmic theater, these theories serve as the scripts, telling us the story of our universe's past, present, and potential future. But remember, these are theories, educated guesses based on our current understanding and observations. The universe, in its infinite complexity, still holds many secrets. As we continue to explore the cosmos, who knows what new theories we'll uncover? As we prepare to conclude, remember that the journey to understand our universe doesn't terminate here, and your quest with us should continue. If you've learned something new and found the theories we discussed as engaging as we did, we urge you to click the like button and voice your opinions or favorite theories in the comments section. You might have your own theories or inquiries about the ones we discussed. We are eager to hear from you, so feel free to contribute to the conversation. Be mindful that every comment, every query, and each shared video enhances our communal comprehension of this magnificent cosmic drama we are all participating in. Importantly, if you haven't already, subscribe to our channel and activate the bell icon so you won't miss our future explorations into the cosmos's enigma. And finally, you're acquainted with someone who shares your fascination with the universe. Why not share this video with them? After all, traversing the universe becomes even more thrilling when shared with loved ones. We appreciate your company on this celestial journey. Until we meet again, keep your eyes fixed on the stars and never stop exploring.